Muito boa tarde, então. Estamos de volta para continuar. Agora, quem vai fazer a apresentação é o Miguel. Miguel vem falar sobre, então, a expectativa de ter usinas de grande porte em tensões mais elevadas. 1.500 volts é uma tendência e a First Solar, então, já tem um módulo nessa tensão. E o Miguel vai nos falar um pouco mais sobre isso. Então, welcome to Florianópolis, Miguel, and the floor is yours.
Muito obrigado. Eu não falo português, so I'm going to speak Spanish. I'm going to speak English. So, thank you very much for coming and to listen to us. And I just want to start with a quick introduction about myself. I am a project development engineer for First Solar. I am responsible for coordinating pre-engineering studies, construction planning, energy simulations, and conceptual design and cost estimates in support of business development and project development initiatives in Latin America. I have been working in the solar industry since 1993, back with Kyocera Solar, Power Light, Sun Power, OptiSolar, Solar World, and I always work on the execution side as a project manager and construction manager, and that experience executing projects is what I'm bringing now to First Solar on the front end to help to prepare proposals that add more value and that are more realistic from the technical point of view for both for First Solar and our clients. So the presentation that I'm going to do this very fast, because while I was here listening to Kendra and looking at the audience, I thought that you may be interested also to learning a little bit about project execution and pre-engineering studies and some of the aspects that need to be taken into account when designing PV power plants that will have an impact in cost and performance in some way. So I have a second presentation that will be a little bit long also. So I'm going to start right now, and after the first one, at the end of the first one, we will go and have a Q&A session, and then we will go to the next one. So, all right. So we are going to talk very briefly about, I want to show the difference between, or the cost advantages that we have when we compare a 1,000-volt system versus a 1,500-volt system. And for that, we have chosen a case study from a real project from Brazil, from the Bahia area, that was subscribed on the EPE, and they have a ficha de dados with all the energy and the commitment, the filme energy and the power commitments. And I'm going to make show a main comparison between the parameters, do a cost comparison, material and labor, and then show a slide where you can see the differences in material quantities between 1,000 volts and 1,500 volts. So here we have so we have the typical chart that represents the firm energy for a project based on the ficha de dados on the EPE. The red line, that is the firm energy, and the black horizontal line is the upper limit, represented is 15% of the firm energy. The yellow line at the bottom is the lower limit, minus 10%. I will not go into the details about the commercial implications of that, but you should know that you always want to have the output of the plant during the 20 years below the upper limit and above the firm energy. That is where you can have the better returns. So the solid blue line represents the energy output over 20 years for a project that uses crystalline silicon modules with the PERC technology, 360 watt modules, and the green line represents the output of a system from First Solar using Series 417 watt DC modules. We wanted to match the energy output and then have that as a reference, and from there see what parameters will change. We decided for this exercise to avoid going above the upper limit. This is a real case that a client showed to us, so they were going a little bit above the upper limit, so the economics are not optimized for the project. So we started with GR1 on the upper limit. We can also, another way, depending on the motivations that the client may have, is to design the system where the output on GR20 is equal or slightly above than the firm energy. But we're focusing only on the two cases above. So the crystalline silicon case is based on 1,000-volt system. That in our case is based on a 1,500-volt system. So here you have, and I apologize for having some text on the wrong direction, so you can. So we have the two configurations using the same tracker. This is with Next Tracker, yeah, and on the top one we have First Solar configuration. It's a 75 by 3 modules, so there are 225 modules per tracker. The lower one is an 80 by 1, 80 modules per tracker. You can see those are to scale. You can see that there is more material for the tracker on the First Solar case. Do you have a pointer here? Okay. So these boxes here and here, cement here, represent the DC wiring for making the series connections. So in this case, this is a harness where 9 strings are connected in parallel. So we have 9 strings of 15 modules connected to the harness. That means there are only 2 conductors coming out of that. And then this is a jumper which will take those 2 strings all the way to in that string, that harness all the way to the end of the road. In this case, we have jumpers for each series of modules, and at the end of the row we will have 8 conductors here, 4 conductors here. With our system, you can connect 7 columns to a combiner box, whereas with the crystalline system, you can only connect 5 columns to a combiner box. So you can start seeing right there that there is a difference in materials. And we will talk a little bit more about that soon. So summary showing a comparison, a side-by-side comparison. You have the 1,000-volt system for crystalline, 1,500 volts. An important parameter here, and this is the variance, an important parameter here is for the PCS, that is the power conversion system, that is the unit where the inverters and the medium voltage transformer are installed. This line item is the number of inverters. You can notice that there are 27 inverters on both cases. However, because of the voltage, in the crystalline case, they organize those 27 inverters in 14 PCSs, 13 PCSs with 2 inverters, 1 PCS with 1 inverter. This came again from a real case, and in our case, we organize the inverters of 3 per PCS. So we are, nominally speaking, we have 3 MVA PCS in this side. Another important parameter is this one here, and this has to do with the inverter rating. And something that we are noticing here in Brazil and in other countries in Latin America is that both developers and consultants, when they are running PVSYST, they are using the nominal value or the nominal rating of the inverters. So that is that they are not adjusting the capacity of the inverters to elevation and temperature. And that could lead to shortfalls during the project implementation if that is not corrected. In other words, the energy simulations done with the nominal rating will not provide a representative, an accurate value results. Another fact that we are identifying is that typically the simulations are being done with assuming a power factor of 1, rather than, for example, in the case of Brazil, looking at plus minus 0.95 power factor, or in Panama, Honduras, is a different. So that is also that needs to be taken into account, and I invite you to pay attention to that. At the end of this table, we have the cumulative energy after 20 years for both projects. And the first solar project is producing 0.5% less energy than the crystalline one. But if you remember the first slide that I showed, that didn't happen by accident. We decided to lower the output to match GR1 energy with the upper limit, whereas with the crystalline case, they were a little bit over the upper limit on GR1. Even though that we are producing less, in terms of DC capacity, which tells you how many modules, how much PV you will need to buy, we can produce almost the same amount of energy with 8.2% less energy, less PV modules. And that is due mainly to our technology advantage based on the spectral shift advantage and the temperature coefficient that Kendra described earlier. There may be also some efficiencies there in the DC losses because we're working with 1500 volts, but I think the major fact, the more powerful facts are the two that I mentioned earlier. And then you can look at the specific yield, and there is an outstanding 4.7% advantage there. There is, as you could see on the previous slide where I showed the two trackers, there is more material that need to be used with our technology if we look at the mounting system. And that applies also to the labor that is required for that. So, and that labor and those apply to the installation of the PV modules as well. So you have more modules you have to install, you need more labor. So we did a quick analysis, but first of all, this is a waterfall where you see if we assume at 85 cents a watt for price for the 85 cents a watt per a DC watt. So for crystalline silicon, the cost will be around $27 million, and for First Solar will be about $24.8 million. So we're talking about a $2.3 million savings in order to produce the same amount of energy. The story is not the same when you look at the materials, so it's going to be different. But it's not as bad as you may think. So on the right, this is the material quantity, and we're strictly talking about the tracker in this case, where you will need 1.1 times the same amount of tracker that it will be required for crystalline. And assuming that PV module exists, that's another thing. It's a 360 watt, highly efficient, so we will need to see that. But and that is equivalent to $500,000. Not a lot of money, but not too much. And the labor necessary to to assemble that tracker and also to install the additional PV modules that will be required is equivalent to $11,000. This is, all these examples are for a 30 megawatt AC project, which is the typical size that we are seeing here in Brazil. So looking at the savings, $2.8 million in one side, and then less than $600,000 in the other side. So you have $2.2 million, assuming 85 cents a watt. So you can do the numbers from there if you drop the price to 70 cents, for example, which is a number that many people is talking about. I'm not going to go over all the details, but I just want to show, for those that like numbers, you know, how we did this analysis for the labor. We work with the tracker manufacturer who perform an independent labor installation study in Chile. So they hire an engineering firm and they send people to an installation site, and they measure productivity for each one of these activities here. Those are the components for the tracker, and this is the time that it took to install each one of the trackers, the components. So at the end, you know, we get to, for a 30 megawatt project, 13,000 man hours to install 1,150 trackers, so 11.4 hour man hours per tracker. This is for cadmium telluride, our technology. And if you look crystalline silicon, they have less trackers than us and 10.6 man hours. Same apply with PV module installation. So for our technology and their technology, so 5,800 man hours versus 4,900 man hours. So, but still the labor cost is substantially lower than the cost of additional DC. So this is very important from the economic point of view when developing the project, because you are lowering your CAPEX, so in obtaining the same amount of energy. So at the end of the day, what is interesting to you or to the developer is to have the lowest levelized cost of electricity, and you achieve that by increasing your energy output and decreasing your CAPEX, and of course the OPEX as well. And talking about OPEX, so then let's go. This is another detail about the harnesses. So you can see that this case shows our typical configuration of 4 high. This is an 8-string harness where you have strings of 15 modules connected in series. For the fixed tilt and for the tracker, there are 2 different products. Those harnesses can be custom made for depending on the configuration that you have, like the one I showed earlier, with 3 modules high. A snapshot from the AutoCAD. Inline fuses, 4 amps. Those fuses can be replaced in the field. Here there is again the 2 trackers. I wanted to point out that this configuration can be optimized. You can use a harness for 2 series. So basically you will have 4 conductors at the end of the tracker, the same way that you have 4 conductors here. So the delta in cost and labor and materials in this case was very small, so I didn't bother to do that calculation, especially because the difference that we have between the savings and the additional cost is so big, so we can still show that there is there are some important savings by going with 1,500 volts. I don't want you to read this. I just want you to look at the you know, the bigger picture. This is a Pareto chart where we have from more expensive to the cheapest one, all the components that go into a power plant. And the blue column represents the cost. This is for a project that is about 500 megawatts that we are working right now. The red line represents the cumulative percentage here in this secondary axis. We could move the cost of this item up or down, or apply or save any money here, and this will not change the entire equation. So what you want to focus is on the items that represent 80% of the cost of your project. And for that, we just zoom in, and now you can read. So this is your PCSs, the power conversion unit with the inverter and the medium voltage transformer that has 25% of the cost of the project. This is excluding PV modules, okay? Then the second item is the interface between the PV modules and the mounting structure. Then you have more mounting structure here, and then you get to DC electrical wiring for harnesses, and also here, and home runs from combiner boxes to inverters. And those three items are very important, because I want to show you the last slide that summarizes an advantage between 1,000 volts and 1,500 volts. And that will end this presentation for a case that we did in the US. In the US, we are using 4 MVA inverters manufactured by General Electric, 1,500 volts. We are installing those in a very large project that we're building there. And we have used a lot, about 2 gigawatts maybe, of SMA inverters, the 800 CPs. So we are comparing side by side with the same model technology, 2 systems. And in order to compare apples to apples, we extrapolated this and scaled it up to match a 4 megawatt comparison is here. All these components, hardware, mounting, the modules, the tracker structure, those will not change whether you go to 1,000 volt or 1,500 volts. What is going to change is your cable, for example. You have the DC cables that are used for the connecting the strings between modules, and then from the modules to the combiner boxes. You have 2 numbers here. If you want to look at that in length, you are saving 38% in terms of length, or if you want to look at that in weight, because copper, is paid in weight, so you are saving 36% of copper on your harnesses. The DC feeders, which are the conductors that run from the combiner box to the inverter, is only a 15% saving. I didn't start the clock. 15% saving, and the reason for that is because by going to 4 MVA at 1,500 volts, now your arrays are larger. So now you have you save a little bit on the DC feeders, because you have now less combiner boxes, but still now you have longer arrays. Combiner boxes, there is a 50% savings. You go from 40 combiner boxes down to 20 combiner boxes. So, and same with the inverters. I asked you to look at this number with caution, because this is specific for this example, where we are using inverters that are 800 kilowatts and 1 inverter that is 4 MVA. Here in Brazil, we are looking at inverters that are 1,000 volts that are being used in PCSs that are 2 megawatts versus inverters that are 1,500 volts that are used in PCSs that are 3 megawatts. It is possible to have 3 inverters that are 1,000 volts in one PCS. That is very possible, or 4, but that will need to be seen a case-by-case basis. So I think that's it, what I have right now. And by looking at these numbers, then we can think about OPEX, operation and maintenance costs. So by having less numbers, 50% less combiner boxes, then you now you can work more efficiently, and you use less time to troubleshoot the combiner boxes or to monitor to measure the combiner boxes. Same with the PCSs. You have less PCSs and so forth. So before I go to the next presentation, are there any questions?
The inverter guys have a lot of questions.
Martin,
Okay, I saw a lot of numbers that you showed of the PCS, the 1000 volt and the 1500 volts and solution, and I could not always get really the relation between the economics and the voltage that you showed. For instance, the power station, you had 2 SMA inverter compared, which is the 800 kilowatts, the old series from SMA, and you compared it to the new GE 4 megawatt inverter. I think a lot of the benefit also comes from the power size of the inverter itself, and not from the voltage that we are talking about. How do you see this point?
So by having higher voltage, you can also have higher capacity at the output of your inverters. So that's one point. And then with regards to cost, smaller inverters, they need their own cabinets, you need the labor to install those inverters, and you have components that are repeated on, let's say you have 3 inverters, smaller inverters and 1 PCS. Oh, I'm sorry. So you have 3 inverters that are, that each one has components that could be otherwise shared with small modifications, where you could have an economy of scale. Then on the installation side, you can have having less PCSs, that saves costs as well. It helps you to improve your construction schedule. So by having a shorter construction schedule, your general conditions, your cost for general conditions is reduced. So that has an impact as well on the bottom line of the project. So those are, I think, some of the important aspects. So getting into the more technical details on the power electronics and all of that, so that unfortunately is outside my area of expertise. But we will be very, very happy to coordinate a conversation between you and our power conversion team, so that our application engineers, that they will be more than happy to talk to you. Does that answer your question?
Okay, yes, thank you. And another point was also, you had the comparison with the I guess polycrystalline module and the first solar module. At the energy yield, where you have been a lot better. For me, that energy yield increase is also not related to the voltage, because it's most of it comes from the temperature and the spectrum effects.
I agree.
Okay.
Perguntas?
Miguel, in Series 3 model, you have a VOC voltage of around 60 volts, yeah. And for the Series 4 model, you increase a little bit the VOC voltage for almost 85, 88 volts per model. So if we are looking into a project until 1 megawatt, which I'm not able, or since Brazil are not able to offer inverters with 1,500 volts level, if I'm using Series 4 model, I could have strings with less modules, so more strings, compared to Series 3, which you could have a lower voltage. So what should be your comments based on this kind of small scale project for rooftops here in Brazil, which Series 4 could be comparable with Series 3, or Series 3 should be the best option for this kind of case?
Yeah. I'm not, Kendra, is this something that you can help to answer the question? Because I'm afraid I cannot answer that. No, I don't have the answer for that question. I'm sorry.
I have a question about large-scale, utility-scale plants or labor and construction times in the different countries. So you have a lot of experience in the US with multi-megawatt power plants, some experience in Australia, some in Chile, and there is zero experience here in Brazil. So the largest power plants are just a couple of megawatts. How can you compare these countries where you have already installed large systems, and what do you expect that automation and labor time to construction will be here in Brazil, and how it is in all these other countries?
Yeah, that's a good question. When we went to Chile for the first time, we didn't have, or Australia, we didn't have any experience about labor. So what we approached this situation from different angles. So we commissioned construction productivity studies on one side. We meet with attorneys where we learn about the labor law requirements, so we can understand the labor rate structure with all the different burden that has to be added. And we also meet with construction companies, like the case of CdTe and Araxá, for example, where we work together, and we went to the US and they look at how our plants are built. They were trained with our different functional groups. Then we went to a project site to see each one of the construction activities, how they were happening. And then on our way back to Florianopolis, we sit with them where we learn about labor productivity in the state of Bahia. We learn about labor composition, the different rates. And once you have that information, then what you do, you look for construction activities that are similar, that are the same in any country, right? So installing a conduit, digging a trench, and you get the specifications, and you look for historical data for productivity for those activities. Typically, productivity is affected by the regulatory environment, what are the laws, what type of unions are there, and also because of the type of tools and equipment that you may have available. So we do our best to capture a productivity rate that we think makes sense, and then we do our cost estimates and project planning with that information, and we know that baseline is going to change. And we see that in Chile. We saw that in Chile already, where we finished a 140 megawatt plant. We had a baseline, and when you compare that with the actual line, we actually have better productivity than what we thought. So now, Luz del Norte productivity is going to become, that's the project in Chile, is going to become our baseline for Chile. So in Brazil, we will do the same. We will just do our best.
How does that compare with the US and Australia?
Compared with the US, the productivity in Chile is less than the US.
How much less? You have
we were using 1.5, 1.75. So there is some caveat in the project that we have in Chile. We use we call it a crew of gypsies, or gun for hire. It's a company that is traveling all over the world, and they have installed about 1.2 or 2 gigawatts of projects globally, and it's the same group of people. So we had a mix of them plus local workers. So we are right now working to try to to clean up the noise that they may have added, and that's why our productivity looks so good. So, but that's in India, for example, productivity is low and labor is very, very cheap. So productivity, labor cost drives also our design and our products. So mounting systems, we will do mounting systems for India that are very cheap and labor intensive, because labor is very cheap. But for the market in Brazil, where labor is not cheap, so we will propose a different mounting system. So something that that is important to know is that First Solar in Brazil is not planning to do EPC. We're just doing PV module supply. So we're talking to different EPC companies like CdTe and others, where we are basically, transferring information with them and answering questions to anyone that is interested in learning from us how to execute these projects.
Okay, now I have a question for Araxá Solar. Vocês acham que o módulo, com as características do módulo de filme fino desse tipo, com menor potência, menor área, vai levar a mais ou menos trabalho de montagem? Como é que é a expectativa de vocês com relação à automação e o tipo de mão de obra que vai ser usado e o tempo para realizar uma usina de porte de 30 megawatts com módulo de filme fino?
Nas análises que nós já fizemos, com um trabalho conjunto com a equipe da First Solar, o ganho da produção de energia com 1.500, com a solução de 1.500 volts, ele ainda fica num saldo positivo em relação aos custos, como o Miguel demonstrou. Então, a gente entende que é necessário uma adequação de todos os fabricantes para essa tecnologia. Hoje nós temos poucos fabricantes ainda disponíveis, Temos GE, temos, Maurício, me lembra aí mais alguns fabricantes? SMA, né? Exato. Então, como é tudo muito novo, essa é a tendência, e a gente entende que os próximos leilões, com a vinda da First Solar aqui para o Brasil, é a solução que deve ser adotada com certeza em termos de produção de energia e custo, sem dúvida.
Mais alguma pergunta?
From the Pareto graph, you said that the module was out of the comparison. It was the cost was not there. But when you showed the cost, the 25 and 24, in that comparison, the module was inside or not?
Yeah, that was you say the millions, when I mentioned that from 27 millions to...
Yeah.
That is just modules.
Oh, they're just modules?
Just module for a 30 megawatt project, assuming 85 cents a watt. So...
Okay. You assumed the same cost for crystalline and your First Solar, and so you have less quantity modules, so that's why you have that smaller CAPEX.
Yes, and that is a kind of rather simplistic way to that I presented there. That the reason, we are using 85 cents, and it should be less. With crystalline silicon, this is a high efficiency module per technology, 80.7% efficiency. That PV module in the US in Q2 2016 will not cost less than 85 cents. In Brazil, will be more expensive. Yeah. To sell it and make money. You can sell it cheaper and don't make money. And there are many companies that, when you look at the cash position, you can see that they were selling below cost. So, having said that, the savings will be even bigger than what I'm showing there. I'm placing our technology at assuming 85 cents a watt at the same level that the crystalline silicon would be. You can see it, you can look at it that way, or you can say we are bringing down the crystalline silicon to the price of first solar.
Oh.
That's why I say it's a very simple way, too simplistic way to compare them.
Yes, but you have the same efficiency in the modules in your comparison? No.
No, there are different efficiencies, and we have different power rating. So this model is more efficient. This is like 18.7%, I think, and here I think we are 16.1% efficient. But
Yes, that's why you have the minus 8% in capacity. Okay.
Yeah.
That's the efficiency.
But the efficiency.
Yes, they have less modules and less power.
No, it has to do, when you look at, we took the design that was done for this. We didn't create this design of these parameters. This was done by our competition. Okay, one of our competitors. And when I look at their design and I measure the row spacing, the space between rows for the product was, I think, 10% or maybe more than the row spacing that we need to produce the same amount of energy. So that is one of the differences that we found, and that's why there are more modules from First Solar than from our competition, and I'm going to show that here. So this is the number of First Solar modules. 258,000 versus 88,000. Right? So, but we install in a tracker 225 models, and they install only 80 models on the tracker. So that's where. So does that answer your question?
Yes.
Okay, perfect. So if there are no more questions, then we can try to fly over the next slides. Let me see how much time we have for that. We have almost no time. So I'm going to talk a little bit about EPC and pre-engineering and some of the things that we need to look at when we look at projects. This is a quick, highlight about First Solar. There are 10 gigawatts in projects already, in modules already installed globally. We have 3 gigawatts under contract, and we do O&M for a combined fleet of almost 9 gigawatts of projects. We bought a company called Skytron early this year that they bring 3.5 or 4 gigawatts of projects on their O&M and monitoring, and we have our fleet is about 3.5 gigawatts, where we had to provide performance guarantees and do the O&M work. So we are financially strong, and we are listed in NASDAQ stock exchange since 1999. So having said our global presence, this is where we are, and this is the 2 factories that we have. We used to have one in Frankfurt, but no longer since 2011. So let's jump now into EPC. So these are the 11 steps, basic steps for the construction of a power plant. From site preparation, mounting structure installation, and then the electrical work, and then substation and commissioning, right? So, but before we start doing the execution of each one of those activities, will be greatly impacted if the assumptions used for the design or the inputs used for the design are not of good quality. So you can do a 1500 volt system to try to capture savings, but if you don't do your homework on the front end, then you will have a terrible project. So very important is to spend money and time on these 4 pre-engineering studies: geotechnical investigation, pilot tests, topographic survey, and hydrology studies. So for the geotechnical study, you want to count with a set of specifications that you can deliver to geotechnical company so they can perform the geotechnical investigation following your requirements, which are in line with your product specifications. So that way, you know that your product, you are going to obtain useful information. So not every geotechnical investigation will work for what you want to do. It has to be done with a solar project in mind. Load test protocol, you have to have a comprehensive load test where you have to do field test to validate the foundation design, the pipes that you're going to use need to be validated, and you have to take into account the wind load analysis. And with all of that and your product specifications, then you can, with a high degree of accuracy, identify the cost for your project. So real quick, I just want to show a picture here. This is a project in Chile, and this is a typical plan that our geotechnical engineers put together, where they show the locations for the different samples that are going to be taken and the different tests. I'm sorry, the resolution is not good, but those are different tests that are performed, electrical tests, thermal conductivity, and also a standard penetration or excavations that need to be performed, and some chemical tests. So they do that, and the number of tests are determined based on our experience and the total area of the site and the technology that is going to be used, fixed tilt or trackers. You need different protocols depending on what mounting structure you're going to use. And that also comes, with some specifications how to set up the test bench on site and the different parameters that you need to take into account. So geotechnical investigation, very important. Load test and field work, very important, because you can find sites with very different conditions, right? This is the same site that I showed you. So you can see these little rocks here and all over the place. So in that site, we also find a place like this, where you have a hard surface on the top, and then when you keep digging, it starts collapsing. So if you don't, we have seen many developers that they come with a 200-hectare site, and they only have a geotechnical investigation with four pits, and they ask us for a firm price. So that is impossible. So that's why you need to do your investigation, because it will help you to generate the foundation design. Or if you have an advanced engineering team, then you can do some probabilistic analysis, and you can create maps where you identify areas of high risk for foundation, and that allow you to quantify that risk, and then determine what will be your contingency. So with that, you cover on the ground risk. Soil conditions will have an impact on your pile specifications, the weight, and the weight, you pay the weight with money. The corrosion protection with the galvanization. It will have also an impact on the grounding grid, on the ampacity of the conductors, depending on the heat transfer capability of the soil. So there are many things that are involved with the geotechnical investigation that you need to take into account. Plus, you also need to understand what the codes or the norms in the countries ask for. This is an extract from the Brazilian technical norm about wind loading, wind speed, and our engineers created this map where we can, the almost entire Brazil is good for our tracker. There is an area where it's not so good, and in that not so good area only means that we will need to reinforce our mounting structure, making it more expensive. But those are things that you need to take into account. So geotechnical investigation, very, very important. Then you have the topographic survey, where you need to generate a good specification for the survey, the tolerances that you want to see. With that data that you will obtain, you will create a digital terrain model, and then with that digital terrain model and the tolerances that the mounting system have, you can calculate how much earthwork you need to do. And that also means a lot of money, and it means represents risk. So it's not the same to have a topographic survey with 5 meters or 1 meter contours and another with 25 centimeters. So with the topographic survey, we do a slope analysis, and we calibrate that with our mounting system tolerances. So red is very bad, and that means that we need to make that area flatter. So you can see very red in this side. So once we do that, then we go ahead and you have to do a grading plan, and you calculate how much earth you need to cut so you can build your plant. So, and in this case here, you can see that, and you always want to have a balanced site. You want to cut, and that to make flatter the site, but that same amount of dirt, you want to put it somewhere else inside the same site. So you have to, here we have 4.5 million cubic meters of dirt that need to be cut, and 4.5 that need to be filled. So that's a lot of money. So with the digital terrain model and the survey that we did and this analysis, we were able to make a decision where we say we are not going to work here. So look at how much it went down, 366,000 from 4.5 million cubic meters. So that was the difference between making the project viable or killing the project. So if you haven't done a good survey work, it will be impossible to do the digital terrain model. And then hydrology, very important, because even though this is one of our projects in the Atacama Desert in Chile, driest place on earth, never rains. Well, this year we have a snow, and there was a terrible storm that destroyed a town that is 70 kilometers downstream from here. Totally destroyed. Our plant was saved because of this that you see here. This is a canal that we built. It cost $10.5 million to build this canal. But when the storm happened in the Andes, we have only minor damage, like $1.5 million in damages, and that is paid by the insurance. So you see here again how the water came in the canal, protected the site. If you don't have a good hydrology study, then you will have a problem with that. So once you do all that, then you can go to and start construction. You do your site preparation, then you can do the installation of the piles, optimizing your work and the product that you are going to use. For us, we like to use driven piles. That is the preferred, and for many companies, the preferred method. We have about 60 of these machines globally that we deploy to any project that we have, almost any project. And installation goes very fast. You can see 10 or 15 machines on the same project just driving piles. So that's, you can do that if you have done all your engineering. You can do that without being afraid that you're going to hit rock and you're going to, you are not going to be prepared to resolve that. Mounting structures, this is a fixed steel. We designed the product to be assembled only with bolts and nuts and a torque range. You don't have to cut in the field or drill or weld, and that is true for almost all major structure manufacturers. There is minimum, and if you need to do some cutting or drilling, there are work instructions that will specify how to do the work and how to protect the metal. And you think also on the, what is the easiest way to minimize the cost of labor on those sites. So this is in the US, for example. Brazil, I will use a similar product where you want to minimize labor work. So right there, you saw those two guys, they have a structure fully assembled in a minute. So in India, we will use everything separate. So it will take you longer to assemble. You will need 1,000 people there, but it's very cheap. PV module installation, you know, 2 men in Chile. We have a very interesting case. I mentioned this crew of travelers. They are from Bulgaria, so 2 men will install 650 modules in 1 day, a 10-hour day, whereas the Chileans will install only 300 modules in 1 day, a crew of 2 men. So we have, in the US, we have installed 7 megawatts in a week in projects that we have built where we had to move very fast. So, and that is in part thanks to, you know, good front engineering and then having products that are designed thinking about, you know, rapid deployment. This is a power conversion system, very old one. We don't use that anymore. All power conversion systems are mounted on a steel skid. Substations, we do a lot of work on substations. One of the largest one is a 600 MVA substation in the US, 34.5 kV to 500 kV with 333 MVA transformers. So one of the transformers is a backup transformer. So I'm just going to give you some facts about the Luz del Norte project. Building solar plants is not complicated, but it's more a logistic challenge in knowing how to manage a project and how to be organized. And so let me show you what. So there is a lot of materials that will be arriving to the site. This is a combiner box, pre-wired. All the cables you just plug in from the harnesses that come down here, and you very fast and easy to install. And it's a way to do quality control in a control environment once you send this pre-assembled. So there are a lot of trucks arriving to the site, and here there are the facts for the project in Chile that was built in, I think, 12 months or so. So we were receiving, you know, we received 2,100 trucks for that project. For this specific day, 24 trucks, 27,000 modules in 1 day. I mean, that. So you had to be very organized during the execution, otherwise you will have immense amount of materials and a congested staging area. An example of a big project, 500 megawatt Desert Topaz in San Luis Obispo, California. This is owned by Mid-American Holding Company, which is owned by Warren Buffett. We have Agua Caliente, 290 megawatt power plant. Mid-America and Energy own the plant. This is the first plant where we implemented our power plant controller for grid integration. What happened? Okay. This is an 80 megawatt project in Sarnia, Canada, in Ontario. So this took a little bit longer to build because in the winter in Canada. So I'm going to show a voltage event that happened in March 21st last year at the Agua Caliente project. So you have the Agua Caliente project is midway between the nuclear plant Palo Verde and the North Gila substation. The North Gila substation supplies energy to Southern California. So it's a key, very strategic substation. This is a 500 kV line. So what happened here was that on that date, the power plant, the nuclear plant, went offline. And this is the voltage. So you can see that the voltage, immediately the voltage went up because this line becomes a huge capacitor. So the voltage started to go up very fast. And the plant operator asked us to help them to support voltage. So they call us, and so somewhere in the morning at 10 a.m., we started to, we set up our plant controller in voltage mode, and we set the voltage at this level. I don't know why, but that was what we were asked to do, so this level. And then when stabilized, we switched to power factor mode 0.99%. So you can see we were able, the reason why this is possible is because the power plant was properly designed and we were able to inject reactive power. And you can see how the reactive power is fluctuating and in order to try to bring this down and keep the voltage down. And this is at night when the solar plant went off. So you can see that the voltage went up again. We couldn't deliver reactive power with the during the night with the inverters that we have in that plant. The G inverters, we can deliver reactive power during the night, for example. So the red line represents the active power, and the blue line is the reactive power that the plants deliver. And even though we have some big clouds that shaded the plant, you can see that the reactive power, nothing happened there, and we were able to maintain the voltage. This is a first solar, the configuration for grid integration for a plant control system. So you have the PV power plant, the inverters, transformers, switchgear, substation, and then we have real-time controllers. We are measuring all these parameters. We have a SCADA system, we have satellite, imaginary, and we have also other sources of the real-time data, like cloud movement and other things that integrate into our system, and that's how we basically control our plants. And this shows how it basically works. So we control each inverter independently. So in Desert Topaz, the project that I showed before, we have about 1,200 inverters or so. Each inverter is monitored and controlled independently. There is a closed loop of every 100 milliseconds, and we measure at the point of interconnection a number of parameters, compare that with our set points, and then we give instructions to the inverters how to behave. Combining the inverters with a power plant controller and a capacitor bank, you can have a device that is known as similar to a StatCom, not exactly the same, and we can give provide grid support without spending too much money. Here you can see the typical curve for a utility company with the requirements for reactive power that a utility company will have for generators, and this is a typical curve for an inverter. So as you can see, when it comes to absorbing bars, there is no major issue for the inverter. The inverter can do that, but when you have to deliver bars, at some point the inverter response is below what many utilities require. So in order to fix that and make it of a cost-effective way, you want to complement your inverters with a power plant controller and a capacitor bank, which is represented by this yellow line. So you add capacitor bank to complete this little piece only. So that gives you more, add more value to the client. And I'm almost done. So this is an example of a plant without a plant controller. So assuming each one of those blue columns is an inverter, you will need to, all generators have a limit that is set by the utility company or by the system itself of how much power you can deliver. And so you need to, on a power plant, you will need to set your inverters such that the aggregated capacity of them will not exceed that limit. And that's why you fix, it's a set point that you place on the inverter. So what happens is that when on a sunny day it's okay, there is no problem, but there are always clouds, and when you have clouds coming in, you will lose some inverters because of the clouds, or the power rate will go down, and the impact that that is going to have is that your energy output is going to be affected. So you can see here all these valleys. This is due to cloud passage. So basically, this is your fixed setting, but this is your actual output. So all this space between this line and the curve is, energy that you weren't able to deliver. So with a plant controller, what happened is that this setting here is a dynamic setting. With the instrumentation that you have on site and the plant controller, so you can force, when you're losing inverters in one area of the plant, you can force the others to deliver more active power. So without exceeding in an aggregated way the interconnection limit that was set up by the utility company. So this is the output without the plant controller, and this is the output with the plant controller. So obviously you generate substantially more energy. And with that, we're done. I'm sorry for flying, but we weren't planning to have a presentation this long, but I thought that it may be interesting for some of you.
So we still have a few minutes for a few questions, right?
Yes.
Perguntas?
Miguel, one more question. The power plant controller is a First Solar property, so the reactive power and the active power is all developed by First Solar?
Mm-hmm. Yeah. So that's proprietary. There are other companies that have their own plant controller, there are inverter companies that have their own plant controller, but this one that we show is solid.
And what is the interface to the inverter?
We have PLCs that we install in the inverters, and then there is some algorithms that are programming on those PLCs. But we work closely with the inverter manufacturer. So for example, anyone goes to buy an inverter from, let's say, SMA, they will not get the same inverter that we get. Because if we want to do business with you, if we want to do EPC, the inverters that people will buy from you will be different than the ones that we will be buying from you, because we give you some additional specifications.
Do you use open protocol like SunSpec or something like that? Do you know?
I'm not sure. We have a functional specification for the SCADA and the plant controller. I know that the hardware is utility grade hardware. I mean the SEL, the standard Schneider relay, the standard hardware, and the protocols we are compatible with the major protocols used by utility companies. Again, the microphone.
Thank you.
You're welcome. Other questions?
Mais alguma pergunta? Então eu vou passar para a Gabriela para a gente fazer o encerramento aqui. Agradeço a presença de todos aqui e também do pessoal que está nos assistindo pela internet. E a Gabriela vai fazer o fechamento.
Obrigada, Ricardo. Obrigada a todos pela atenção hoje. Queria só mais uma vez agradecer a presença de todo mundo em nome da First Solar, dizer que eu estou aqui à disposição como representante comercial da empresa para responder quaisquer perguntas que vocês tenham, e me disponho também a estar disponível por e-mail, e se quiserem mais informações dos módulos, também é só falar comigo. Obrigada.